This is a problem involving the ideal gas law and reaction stoichiometry. So the problem says hydrogen gas is formed by the reaction of methane, CH4, with water vapor, according to the reaction shown. 25.5 liters of methane at a pressure of 732 torr and temperature of 25 degrees Celsius mixes with 22.8 liters of water vapor at a pressure of 702 torr and a temperature of 125. By the way, you may hear some construction in the background and some lawn maintenance and a truck beeping, but I really just want to make this video. So anyways, I hope it's not that much of a distraction. So the best approach to this is recognize that, okay, I wrote underneath the volume, the pressure, and the temperature pertaining to substance or reactant 1, which is methane. Then I have all the amounts for the second reactant. So whenever you're given an amount of both reactants, we could definitely predict it's going to be a theoretical yield problem. Or in particular, we want to find even further, find the percent yield. Because not only we're given the amount of reactants, but with those, we could find the amount of products if we have both amounts of reactants. But if we find the amount of product, that's going to be our theoretical yield, the yield calculated by us. So it seems the problem seems kind of silly, like it defeats the purpose, because you may be thinking, wait, why do I want to calculate the amount of product, H2, if they tell us the amount of product? Well, again, if they tell you the amount of the third substance and amount of product, it must be an experimental or actual amount. So this given quantity is an experimental or actual yield. So let's continue. So look at this on the left. You're given all the quantities pertaining to gases except moles. So clearly your first step is to calculate the number of moles here. But to do so, you need to convert to the right units. So remember, convert pressure to atmospheres, 760 torr to every 1 atmosphere. To convert from degrees Celsius to Kelvin, you add 273. Good. And then we arrange the ideal gas law, PV equals nRT. So it should be PV over RT. So the moles of substance 1 should be its pressure. 732 divided by 760 is 0.963 times the volume in liters, all divided by the ideal gas constant, R, 0.08206 times the temperature in Kelvin. 25 plus 273 is 298 K. So the number of moles of reactant 1 should be about 1.00 moles of CH4, methane. Excellent. Now we do the same procedure with reactant 2. Okay, so now we do reactant 2. Number of moles of reactant 2 is given by PV over RT. Again, I'm going to take the torr for pressure 2, and I'm going to use 760 torr to every 1 atmosphere. And of course, I'm going to add 273 to the temperature in Celsius. So the pressure is 0.924 for reactant 2. The volume is 22.8 liters. R. The temperature should be 125 degrees Celsius plus 273. This gives 398 Kelvin. So the number of moles of reactant 2 is 0.645 moles of water vapor. Excellent. So whenever you calculate theoretical yield to then find percent yield, if needed, we need our amounts of substances to be reported in grams or moles. We always need moles first because this allows us to use the other information provided, which is the chemical equation, which contains the stoichiometric coefficients. In other words, our coefficients represent moles. So the second step is find the amount of product generated in relation to reactant 1. The amount of product formed from reactant 1 is the 1.00 moles of CH4 good. So we're taking our amount of reactant in moles, and we want to find the amount of product in moles. To convert from moles of one substance to moles of another, we use the stoichiometric coefficients from the balanced chemical equation. Notice that the chemical equation is balanced, so I can say there's 1 mole of methane to every 3 moles of H2. Let me just clean this up a bit. So we're going to say there's 1 mole of methane, and then the chemical equation says there's 3 moles of product. This is the product we're interested in. Remember, there's 2 products. The other one is carbon monoxide, but they wanted the percent yield for H2 because they gave us information pertaining to H2. So we're never going to look at the other product, only this one. So this converts us to being 3 moles of the desired product. Next, the amount of product generated in relation to reactant 2 is given by the following. Our moles of reactant 2, 0.645 moles of water. Next, we use the stoichiometric coefficients. There's 1 mole of water to every 3 moles of product. Let me go back and check that. 1 mole of water to every 3 moles of product. When you type this into the calculator, you get 1.94 moles of hydrogen gas product. So we need to perform the calculation twice for each reactant. And notice how we compare the numbers. Yeah, we get two answers. We get two quantities, two numbers. So the question arises, okay, which one of these amounts represents the theoretical yield? Well, that's always the smaller of the two numbers. So the theoretical yield is 1.94 moles. The smaller of the two numbers. Now, the reactant that gave you that smaller number is the limiting reactant. So limiting reactant is H2O. This just means although methane had the potential to generate 3 moles of product, it's not going to reach that point. It's going to be limited by the water vapor. Since the water vapor is the reactant that runs out of fuel first, the methane will no longer have anything to react with, even though the methane has excess fuel remaining. That's why we picked a smaller number. Again, we could get 3 moles of hydrogen from methane, but it just has nothing to react with when H2O runs out. So finally, the last step would be, we know the actual or experimental yield was the number provided that they measured in the lab. This was given as a volume of 26.2 liters of product at STP. Well, STP means, let me write it below. STP means N is 1 mole, temperature must be 273, pressure must be 1 atmosphere, and the volume must be 22.4 liters. Finally, a thing students must recognize is that you can actually combine any two STP values in combination to produce a conversion factor. So I could say 1 mole of any gas to this volume. So again, the next step is to use a ratio of STP values as a conversion factor. So this is going to be 22.4 liters to every 1 mole. Liters on top cancels liters on the bottom. So in this case, we're dividing. This gives 1.17 moles of product. So finally, the equation for percent yield should equal the actual or experimental yield measured in the lab over the theoretical yield, which is calculated, times 100, tack on a percent sign. Again, this is the experimental, which is 1.17 moles of H2, divided by the theoretical yield, which is, that was the 1.94. And then multiplied by 100 to convert it to a percentage. Also notice how the percent yield is a unitless quantity, except the percent sign itself is kind of like a unit. So finally, when you type this into the calculator for your final answer, you get about 60.3%. So that's the process of percent yield. Again, just recognize the equation and understand the meaning behind it. Why is the numerator experimental and the theoretical is the denominator? Well, just keep in mind the experimental yield should always be less than the theoretical yield. And that's to take into account experimental error in our measuring devices. So in the lab, when you go to measure the amount of H2 or the amount of any substance, well, you have the inherent error from your measuring devices. Sometimes there's spillage or materials stick to the bottom of the container, which impacts your measurements. So the theoretical is is derived through pure calculation. So there's no error, no experimental error that can impact that. So that concludes how to calculate the percent error and use reaction stoichiometry in combination with the ideal gas law.